So recently, a gentleman named Ray Gessner was reviewing a post by Jerry Eisenhower in a Facebook group called the Professional Chimney Sweep Forum.
A great resource, by the way.
Totally. And Ray was just absolutely blown away by the depth of the insights shared in that post. So much so that Ray actually requested we do a full, dedicated discussion exclusively covering Chapter 1 of the seminal publication, Chimney Fires, Causes, Effects, and Evaluation.
Which is, I should add, a remarkably detailed foundational text. It was prepared by the Chimney Safety Institute of America, or the CSIA.
The CSIA, right.
Yeah, it's essentially the Bible for understanding the pathology of chimney systems.
It really is. And we want to explicitly state right at the top of this deep dive that this is dedicated to the education of the entire chimney industry.
We're getting right into the weeds.
We are. We are going deeply, comprehensively into the source material, digging exclusively into Chapter 1, just Chapter 1, section by section, to uncover the vital anatomy and the performance of masonry chimneys.
It's a lot of ground to cover, even in just one chapter.
Oh, absolutely. And before we go any further, we really need to take a moment to specifically thank Jerry Eisenhower.
Yes, his work is vital.
Jerry, thank you so much for your hard work, your incredible documentation, and your massive contribution to the chimney sweep industry.
The documentation in this text is just phenomenal. And our goal today is to take that foundation, and reveal the incredibly complex, dynamic system operating right inside the walls of your home.
We want to completely redefine what you think of when you look at that brick structure on the side of your house. So, okay, let's unpack this.
Let's do it.
Starting with how we even define the standards for building these structures in the first place, because the text outlines this massive historical shift in how engineers and builders actually think about chimneys.
Right, the philosophy has completely changed.
Yeah, historically, building a chimney was all about very rigid material specifications. The rules would just dictate the ingredients. They would say, use this specific thickness of brick, use this exact type of mortar, build it to this height, and supposedly, you were done.
You followed the recipe, you got a safe chimney. That was the thought.
Exactly. But the source material highlights that this recipe approach is completely obsolete. Today, the focus has entirely shifted to performance.
And that is a critical distinction to make right away. In the past, codes basically treated a chimney like a static object.
Like a wall.
Right, like a wall. But the modern approach recognizes that a chimney is not static at all. It is a system of highly interrelated components.
So it's not just a pile of bricks.
Not even close. It's about how those materials perform together under specific and often, violently extreme conditions.
I was trying to conceptualize this shift, and I think it's a lot like buying a car, right? You don't just walk into the dealership and ask the salesperson, excuse me, what specific alloy of steel is the engine block made of?
I mean, maybe a few hardcore gearheads do.
Well, yeah, maybe. But mostly, you ask how the car performs. You want to know what happens when you hit the gas on the highway to merge into fast traffic. You want to know how the anti-lock brakes respond if you, hit a patch of ice at 60 miles per hour.
You care about the performance under dynamic stress.
Exactly. You are buying the outcome, not just a list of metals.
Precisely. And treating the masonry chimney with that exact same performance-based mindset is vital to understanding Chapter 1. Every single component plays a part.
From the ground up, basically.
Yeah, from the concrete foundation footing deep in the ground, to the thimble, to the flue lining, all the way up to the chimney crown on the roof. They all play a highly specific role in the overall success of this system.
And if one fails?
If one part fails to perform its function, the entire system is compromised. You really have to evaluate its ability to perform its intended function safely, efficiently, and consistently over decades of abuse.
Okay, so if a modern chimney is judged entirely on performance, it forces us to ask, well, what exactly is it performing its duties against?
Right. What is the threat?
Yeah. What are the actual functions? The text is very precise about the terminology here, and I realize I have been using these terms completely interchangeably my whole life. Let's start with the big one. What is the fundamental difference between a heating system and a venting system?
It helps to think of it as, a hierarchy of operations.
Yeah.
The heating system is the overarching umbrella.
So it's the whole package.
Exactly. It's the entire holistic package of interrelated components that produce, distribute, and exhaust heat for your building.
Okay, so that includes the appliance itself.
Yep, the wood stove, the oil furnace, the fireplace,
Right.
plus whatever distribution system exists, like ductwork or radiators.
Yeah.
And finally, the venting system.
Got it. And the venting system is just a part of that.
Right. The venting system is specifically the series of open, continuous conduits that carry the exhaust from the appliance to the outside atmosphere.
Okay, let's talk about that exhaust because the text refers to it as flue gases. And if you ask the average person on the street what comes out of a chimney, they're going to say smoke. Just fluffy gray smoke.
Which is a huge understatement.
Right. Reading the source material, I realized that calling it smoke is a massive, almost dangerous oversimplification.
Oh, it absolutely is.
Yeah.
Flue gases are a highly complex, aggressive chemical cocktail. You really have to look at what happens during combustion.
Because it's not just making things hot.
Now, when you burn fuel, whether it's cordwood, natural gas, or oil, you are not just creating heat, you are initiating a profound chemical reaction.
And the byproducts of that go up the flue.
Exactly. The products of that combustion, along with any excess room air that gets pulled into the draft, travel up the venting system.
And the text specifically breaks down what is inside that stream. It is not just invisible gas.
Right. I mean, it contains invisible gases, sure, like carbon monoxide, carbon dioxide, and various nitrogen oxides. But crucially, it also contains condensable liquids.
Wait, condensable liquid? So it's wet.
Yeah. Depending on the fuel, there is a massive amount of water vapor in that exhaust. As that vapor travels up the chimney and cools, it can condense back into a liquid state right on the walls of the flue.
Wow.
And it's not just plain water, it's acidic water. Furthermore, the draft is carrying tiny, unburned liquid droplets and solid, microscopic particulate matter.
Which means the venting system isn't just a passive pipe letting hot air float away. It is an active, highly volatile waste management highway.
That's a great way to put it.
You have corrosive acids, physical soot particles, water vapor, and highly flammable organic compounds all rushing up this dark tunnel together.
Exactly. It is a highly active, physically dense stream of matter. And because of the moisture and the acids, it is incredibly corrosive to the very masonry materials trying to contain it.
That paints a much darker, dirtier picture than a cartoon chimney puffing white clouds.
Oh, for sure.
And speaking of the structure containing it, the text also draws a hard line between the word chimney and the word vent. Again, I always thought these were just synonyms. What is the actual distinction there?
Well, a vent is a manufactured, highly engineered product designed for a highly specific, very narrow purpose.
So it's specialized.
Highly specialized. It is intended only to serve a specific type of appliance, like, say, a modern high-efficiency gas furnace, under very tightly controlled and defined conditions. It is not versatile at all.
And a chimney.
A chimney, however, is a structure that is designed and constructed to form one or more vertical passageways, which we call flues, to the outside atmosphere. A chimney is designed as a general-purpose venting system.
General purpose meaning, what, it has to be ready for anything?
Precisely. It is built to be robust enough, heavy enough, and durable enough to handle a much wider class or range of service compared to a dedicated vent.
Because appliances change, right?
Exactly. You might have a wood-burning fireplace connected to it for 20 years, and then the next homeowner might run a completely different type of appliance into it. The masonry chimney has to have the foundational integrity to handle a broad spectrum of thermal and chemical abuse.
And the text breaks down these general-purpose chimneys into three main categories: metal, factory-built, and masonry. It explicitly notes that metal and factory-built systems are distinct entities with their own engineering realities.
Which is fascinating stuff, really.
It is, but we are going to leave those aside for today, because for this deep dive, based on Ray's request, we are dedicating ourselves completely and exclusively to the heavy hitter masonry chimneys.
The classic brick, mortar, and block structures built right on site.
Yes, which is highly appropriate because masonry chimneys are where some of the most complex, long-term thermal dynamics occur in residential construction.
Absolutely. The sheer mass of a masonry chimney completely changes how it interacts with heat, which leads us right into the core design philosophy of these structures.
Right, because you can't just assume everything is going to work perfectly.
Exactly. When an engineer or a mason is designing a masonry chimney, they are not just designing it for a perfect, crisp autumn evening when the homeowner builds a flawless, highly efficient, well-oxygenated fire.
Right, you are not designing for the best-case scenario. You have to assume things will go wrong. You are essentially anticipating failure.
You have to. The performance requirements dictated by modern codes must anticipate both appliance malfunction and operator error. Because, let's face it, people make mistakes.
Oh, all the time.
They burn wet wood, which creates massive amounts of creosote. They leave draft dampers wide open and just walk away. Mechanical thermostats on stoves malfunction.
So the chimney takes the brunt of all that.
Exactly. Therefore, the chimney must be designed with the structural capacity to handle continuous operation at hotter than normal temperatures, as well as brief, intense episodes of extreme temperatures, like a chimney fire.
And here is where the focus of the engineering completely flips, right?
Yes. As the expected temperatures inside the flue get higher and higher, the design focus actually shifts outward.
Outward, meaning away from the flue itself.
Yes, it moves from just protecting the chimney structure itself from cracking to protecting the combustible materials surrounding the chimney from actually catching fire.
Okay, here's where it gets really interesting. And honestly, this was the part of the source material that made me stop, put my notes down, and reread the page twice.
I know exactly what you're going to say.
We mentioned it right at the top of the show. It is this concept of the pyrophoric carbon phenomenon. We are talking about the wood framing of the house itself, the floor joists, the ceiling rafters, the wall studs that are physically adjacent to the masonry chimney. What exactly is happening to that wood over the lifespan of the house?
It is undergoing a slow, invisible, and highly dangerous chemical and physical transformation. Wood, in its natural state, has a relatively high ignition temperature.
Right, it doesn't just burst into flames on a warm day.
No, you usually need an open flame or intense direct heat, somewhere around 400 to 500 degrees Fahrenheit, to get a piece of structural lumber to actually ignite.
Okay, so 400 to 500 degrees.
But when wood is subjected to continual intermittent exposure to even moderate heating from a hot chimney over a long period of time, it suffers from a drastically decreased resistance to ignition.
Define moderate heating, because this is where I struggled when reading Chapter 1.
The cycle goes like this. The homeowner burns a fire. Heat transfers through the brick into the surrounding wood. The wood heats up, then the fire goes out, and the wood cools down.
And then the next day, it happens again.
Exactly. This on and off heating cycle slowly bakes the natural moisture and the volatile organic compounds out of the cellular structure of the wood. Over months, years, and decades, the cellulose and lignin in the wood actually break down.
It's basically getting cooked.
Systematically carbonized. It is converted into what is called pyrophoric carbon.
Wait, let me stop you there. I have to push back on this, or at least ask for you to break down the physics, because the numbers in the text blew my mind. When you say moderate heating, my brain immediately goes to, I don't know, a pizza oven. 500 degrees, 600 degrees.
Sure, that makes sense intuitively.
But the text explicitly states that a temperature rise into just the 200-degree Fahrenheit range can be enough to initiate this transformation. 200 degrees is boiling water. It's a hot cup of coffee. How does a temperature that low fundamentally alter the cellular structure of a piece of wood? That totally defies common sense.
It absolutely defies our everyday intuition, but the chemistry is incredibly well documented. It is not about the sudden application of intense heat. It is about the duration and the intermittent nature of the exposure.
So pouring coffee on a 2x4 for 10 years.
Essentially, yes. Think of it like slow roasting something at a very low temperature. The constant cycling of 200-degree heat provides just enough energy to slowly break the chemical bonds within the wood's moisture and resins. The wood essentially undergoes a low-grade pyrolysis.
Pyrolysis meaning it's decomposing due to heat, but without actually burning.
Exactly. It breaks down thermally without combusting. And as it loses those volatile compounds, the material that is left behind, this pyrophoric carbon, changes on a molecular level.
And it becomes dangerous.
Very dangerous. It develops self-heating properties, meaning it can actually begin to oxidize and generate its own internal heat, and it becomes incredibly reactive to oxygen.
Wow.
In this degraded state, the wood is literally primed and ready to burn. It has been perfectly prepped for combustion. And the terrifying part is that it is just sitting there in the concealed, unventilated areas of your home.
Like inside the floor and ceiling assemblies.
Yeah, or inside the wall cavity where the chimney penetrates to the outside. It's just waiting.
Waiting for a trigger.
Yes.
Oh.
Because the ignition temperature of the wood has been artificially lowered so drastically over the years, it no longer takes a massive inferno to set it off. The safety margin is completely gone.
So what finally triggers it?
One accidental overfiring of the wood stove, or maybe a relatively small, short-lived chimney fire that raises the surface temperature of the brick just a little bit higher than normal, that can provide the exact amount of thermal energy needed to ignite that pyrophoric carbon.
So the wood doesn't even need to touch a flame.
Not at all. The radiant heat alone will cause it to spontaneously combust.
That is absolutely terrifying. It's like a slow-motion fuse burning inside your walls for a decade before it finally hits the powder keg. And the homeowner has absolutely no idea it's happening because everything looks completely fine on the outside of the drywall.
And this is the absolute core reason why airspace clearances around masonry chimneys are legally mandated by building codes.
Oh, that makes so much sense now.
Right. When codes say you must have a 2-inch airspace clearance between the outside of the chimney and any combustible material, it is not a suggestion. It is a strict engineering requirement to prevent thermal bridging.
Because if the wood is touching the brick,
If you do not have that clearance, if the wood is touching the brick, that wood is actively baking every single time you light a fire.
which makes perfect sense of why the text hammers so heavily on chimney anatomy. To understand how we try to prevent that heat transfer, we really need to take a mental tour of the physical construction of the masonry chimney itself.
Let's do it.
We need to break down the critical components that make up this system. Let's start down near the bottom. Picture the basement or the lower level of the home, the clean out.
Yes, the clean out. Every chimney, regardless of what type of fuel the appliance burns, requires physical provisions for cleaning and inspection. Most building codes specifically mandate a clean-out opening for each individual flue at the base of the chimney.
And the text gives a very specific hard measurement here. It says the cleanout must be located at least 12 inches below the lowest appliance inlet opening.
That 12-inch rule is crucial.
Right, and I want to understand the why behind this. Why that specific distance? Why the 12-inch rule?
Well, it serves two highly functional purposes, both related to the physics of maintaining the system. First, it provides the necessary physical access for a chimney sweep.
For cleaning.
Right. When a sweep is cleaning a chimney, they are using brushes to scrape soot, ash, and hardened creosote off the walls of the flue, starting from the top down. All of that debris has to go somewhere.
Gravity does its thing.
Exactly. The 12-inch drop provides a dedicated volume of space, a collection zone, for that swept debris to fall into, so the sweep can actually reach in with their tools or a vacuum and remove it. You need room to work.
Makes sense. And what's the second purpose?
It acts as a critical buffer zone during normal operation. As I mentioned, debris naturally falls down the chimney over time. Soot flakes off, maybe a bird's nest drops down, or older masonry crumbles.
Stuff just accumulates.
Yes. It creates a dedicated space for this debris to accumulate without immediately blocking the inlet, where the heating appliance is actively trying to exhaust its dangerous gases.
Oh, I see.
If the bottom of the cleanout was completely flush with the appliance inlet, even a small handful of swept debris or fallen soot would instantly choke the appliance.
And that would push the exhaust back into the house.
Instantly. It would cause toxic flue gases, including carbon monoxide, to immediately back up into the living space. So that 12-inch pocket is a literal lifesaver.
Wow. And we should talk about the doors on these cleanouts, because when I picture a cleanout door, I just picture like a little square of flimsy metal in the brick. But they can't just be loose-fitting pieces of tin, right?
Absolutely not. They are a critical seal in the venting system. Codes require these doors and their frames to be made of ferrous metal, stainless steel, precast concrete, or another highly durable, approved, non-combustible material.
They have to be tough.
Very tough. And crucially, they must secure tightly in place.
Why is the tight seal so important at the very bottom of the chimney? I mean, it's just the basement.
Because a chimney operates on draft, which is essentially negative pressure created by the buoyancy of hot gases rising. The chimney is constantly trying to suck air up.
Right, like a straw.
Exactly. If a cleanout door is loose, cracked, or completely missing, it introduces massive amounts of uncontrolled room temperature air into the very bottom of the venting system.
And that messes up the draft.
It instantly destroys the draft, making the appliance run terribly. But worse, if you have a chimney fire up in the flue, that open cleanout door acts like a massive carburetor.
Oh, man.
Yeah, feeding the fire with an endless, uncontrolled supply of oxygen from the basement. It will turn a small flue fire into a roaring jet engine.
Okay, so that is the base. Let's move up the wall to where the appliance actually connects to the chimney system, the thimble.
The thimble is critical.
I picture this like a high-temperature docking station. It is the literal port where the black connector pipe from your wood stove or furnace plugs into the masonry wall.
That is a perfect analogy. The thimble is a tubular sleeve embedded horizontally into the vertical masonry chimney wall. It is designed to receive the end of the chimney connector.
What are they usually made of?
They're usually made of the same vitreous fire clay as the main vertical flue lining, although they can sometimes be made of specific metals. But the most crucial safety detail regarding thimble construction, and this is an area where installations frequently fail in the real world, is its physical length. and how it integrates with the rest of the system.
Right, the source material emphasizes this incredibly heavily.
It explicitly states that the thimble absolutely must extend continuously from the outside face of the chimney wall all the way through the brick or block to the inside face of the vertical flue lining.
It can't fall short.
It cannot fall short.
Yeah.
And furthermore, it must be permanently cemented in place using the exact same high-temperature, non-water-soluble cement that is used for the vertical liner joints.
I want to visualize the failure point here. What exactly happens if the mason gets lazy or the thimble is just a little bit too short? What if it doesn't reach all the way to the inside face of the clay liner?
If it falls short, even by a fraction of an inch, or if the wrong type of mortar is used and it degrades and crumbles away over time, you have created a physical gap in your docking station, a massive leak. And remember what we said about those flue gases. They are hot, they are toxic, and they are highly pressurized. When the appliance exhausts into the thimble, those gases will hit that gap and escape.
They don't even make it to the flue.
Right. They will bleed out of the exhaust stream and enter the hollow, unventilated space between the inner clay liner and the outer brick wall.
And that hollow space isn't meant to handle raw exhaust.
Not at all. Once the hot gases are trapped in that outer masonry cavity, it is a very short, very fast path to transferring fatal amounts of heat through the brick and directly into the surrounding combustible house framing.
Which takes us right back to baking that wood into pyrophoric carbon. It is all connected.
Exactly.
The gap in the thimble feeds the heat into the brick, which bakes the wood stud 2 inches away over the course of 10 years, lowering its ignition temperature until one cold Tuesday night, the homeowner builds a slightly larger fire than normal, and the wall spontaneously ignites.
Precisely. The system fails because a single microscopic component, a quarter-inch gap in the mortar of the thimble, failed to perform its function of total containment.
That massive risk of heat transfer highlights a much larger historical problem discussed in the chapter. The entire structural integrity of the chimney relies on containment.
Total containment, yes.
And historically, we didn't always have a reliable way to contain that chemical cocktail. Which brings us to the history of the flue lining itself. This is where the engineering history gets genuinely fascinating.
Surprisingly long history.
Yeah, because when I think of building codes or strict fire safety standards, I tend to think of modern 21st century regulations. But the concept of requiring an internal flue lining to contain the exhaust is not a modern invention at all.
Far from it. The industry's recognition of how vital a continuous flue liner is goes back over a century. The text cites incredibly early insurance documents, specifically the 1909 Crosby-Fiske Handbook of Fire Protection.
1909. That is the era of the Model T Ford.
Yes. The Crosby-Fiske Handbook is the predecessor to the modern National Fire Protection Association, or NFPA, handbooks. Even back in 1909, after seeing cities devastated by fire, the insurance engineers mandated that all chimneys must be built of solid rock with the inside joints struck completely smooth.
Just to reduce friction?
Partly, but crucially, they mandated the chimneys had to be provided with a hard-burned flue lining. 7 years later, the 1916 Insurance Engineers Handbook went even further, explicitly requiring sealed joints and mandating that the internal lining extend the full length of the chimney, from the very bottom to the very top.
So if we connect this to the bigger picture, why were insurance engineers from 100 years ago so obsessed with this specific detail? What is the actual fundamental purpose of the liner? Why isn't a thick wall of brick enough?
Well, primarily because a brick wall is naturally porous.
Right.
And those mortar joints are incredibly vulnerable to acids. The liner serves two distinct but equally critical physical purposes.
Containment is the first one, right?
Right. The primary purpose is containment. The liner must contain the fire, the intense heat, and those highly dangerous pressurized products of combustion, keeping them safely isolated inside the vertical flue passageway until they exit the top of the chimney.
And the secondary purpose?
It is the protection of the chimney structure itself. The liner physically protects the outer masonry walls from the corrosive acidic moisture found in the flue gases.
Because if the acid hits the brick...
If acidic water vapor condenses directly onto bare brick and mortar, it will dissolve the mortar over time. The liner also protects the masonry from premature deterioration caused by thermal shock.
Thermal shock being sudden temperature changes.
Exactly. When a chimney goes from freezing cold to incredibly hot in a matter of minutes, the materials expand violently. Without a durable liner to absorb that initial shock and contain the acid, a brick chimney will literally rot and tear itself apart from the inside out.
And yet, despite the fact that insurance handbooks have been screaming about this since William Howard Taft was president, the source material points out a stunning, almost unbelievable detail about human nature and the construction industry.
It's pretty shocking.
To this very day, there are still massive masonry chimneys being built completely unlined.
Yes, unfortunately.
And even worse, the text notes a deceptive practice where some builders will just stick a single fake clay tile section onto the very top of the chimney just to fool the local building inspector.
I know, it is a shocking level of negligence. Yeah. But it happens because of economics and the nature of the structure. Proper flue liners are expensive. Installing them correctly joint by joint as the chimney is built up takes significant time and highly specialized skill.
It's hard work.
Very hard work. And since the inside of a chimney is a black hole, as we discussed at the start, unethical builders assume no one, not the homeowner and not a rushed building inspector on the ground, will ever look deep enough down the shaft to notice the deception.
They just look at the top.
Right. They build a hollow brick tube, stick a $20 piece of clay on the top put, and walk away.
It is mind-boggling. You are essentially building a bomb in the center of the house to save a few $100s. But this exact type of widespread negligence and the resulting catastrophe of house fires is what led to massive government interventions, right?
Correct. Despite the written standards existing since the early 1900s, by the time we reached the mid-20th century, the fire statistics were grim. Houses were still burning down at an abysmal rate, and the root cause was overwhelmingly listed as defective chimneys.
The codes were just being ignored.
The rules existed on paper, but they weren't being enforced, or the older unlined brick chimneys from the 1800s were simply failing en masse as people upgraded to hotter-burning modern heating systems.
So the government stepped in?
This crisis prompted the federal government, specifically the Housing and Home Finance Agency, to step in and sponsor major, definitive scientific research.
And the text highlights the specific work done at the National Bureau of Standards by two researchers, Robert K. Fulman and Nolan D. Mitchell.
Yes, Fulman and Mitchell. Their research in the late 1940s was the crucible that forged our modern scientific understanding of chimney safety. They didn't just look at statistics, they built physical testing apparatuses.
Like full-scale test chimneys.
Yes, they constructed various types of masonry chimneys in a laboratory setting, some lined, some unlined, some with varying degrees of airspace clearance, and they surrounded them with wooden mock-ups of house framing.
They basically built fake sections of houses just to set them on fire.
Exactly. They instrumented the wood framing with thermocouples to measure the exact temperatures transferring through the brick. They ran sustained fires, they simulated overfiring, they simulated chimney fires.
Then what did they find?
Their highly documented tests proved, beyond a shadow of a scientific doubt, that unlined chimneys or chimneys with degraded liners were directly and immediately responsible for transferring lethal amounts of heat to house framing.
They proved the pyrophoric carbon theory in a lab.
They proved that without a barrier, the heat transfer is inevitable. Their exhaustive reports led to the unequivocal, non-negotiable building code requirements we have today. You absolutely must have a continuous intact flue lining, and you absolutely must have absolute verified airspace clearance between the outside of the masonry and any combustible structural materials.
Which brings us to the modern era of how we actually achieve that containment. How do we build these liners today to survive the abuse? This is covered in depth in the chapter. And let's start with the undisputed heavyweight champion of the last 70 years, the clay flue lining.
Ah, yes.
The classic.
When I picture a chimney liner, this is what I picture. Those heavy, orange, terracotta-looking square tubes.
Yes. Standard clay liners are the absolute workhorses of the residential chimney industry. But they are far more sophisticated than simple terracotta flower pots. They're manufactured from highly specific engineered mixtures of fire clay, surface clay, or shale.
How are they actually made to withstand the chemical and thermal abuse? The manufacturing process involves extruding this heavy clay mixture into the tubular shape, drying it, and then firing it in massive kilns at extremely high temperatures for an extended period.
To bake it all together.
Right. The heat in the kiln is so intense that it causes a physical and chemical change in the clay. It partially melts the silica components within the clay matrix, fusing the particles together and transforming the material into a vitreous state.
Vitreous meaning glass-like.
Exactly. It becomes incredibly dense, non-porous, and glass-like on a microscopic level. This vitrification is what makes the clay highly resistant to both extreme heat and, crucially, the corrosive dissolving acids present in the flue gases. It acts as a hardened shield against the chemical cocktail.
But the text notes a really interesting logistical and economic quirk about these clay liners. Even though they are the standard used in almost every masonry chimney in America, there are actually fewer than 20 major manufacturers left in the entire country producing them.
Yes, and their locations are not based on market demand. They are entirely dictated by
Oh,
geology.
really? Because of the clay?
Yes, you cannot make a vitreous fire clay liner out of just any mud you find in the backyard. These massive manufacturing plants tend to be heavily concentrated near specific, substantial, natural geological deposits of the exact raw fire clay and shale needed to formulate the product.
That makes sense.
It is a highly specialized, geographically dependent, heavy industry. Transporting millions of pounds of finished clay tile across the country is expensive, which heavily influences regional building practices.
But whether the liner is made of traditional clay pulled from the earth or a newer alternative high-tech material, every single lining system has to prove its worth to the safety authorities. And that brings us to the ultimate proving ground highlighted in the chapter, the UL 1777 testing gauntlet.
The gauntlet, that is the perfect word for it.
This is the safety standard developed by Underwriters Laboratories specifically for chimney liners. And reading the testing protocols in the source material, I mean, it is brutal. I'm amazed any physical material can survive this process.
It is designed to be punishing. The UL 1777 standard is engineered to simulate the absolute worst-case catastrophic scenarios a chimney could ever face in the real world, including a full-blown sustained creosote fire.
How does the test start?
To achieve a UL 1777 listing, the manufacturer's liner is installed in a standardized, heavily instrumented test chimney in the laboratory.
Walk me through the phases of this test because it escalates wildly.
The first phase is testing for continuous, sustained high heat. They pump 1,000 degree Fahrenheit flue gases into the liner, and they hold it there continuously for up to 8 straight hours.
8 hours at 1,000 degrees. That is enough to melt lead. And that is just the warm-up phase.
It is just to establish a baseline of thermal saturation. Then they crank the heat up, they elevate the flue gases to 1,400 degrees Fahrenheit, and hold it there for a full hour.
Simulating what, an appliance that's broken?
Exactly. Simulating an appliance that has completely malfunctioned and is running wide open. And if the liner survives that hour without cracking, crumbling, or failing, they subject it to the ultimate thermal shock. They simulate a raging chimney fire.
This is the crazy part.
They initiate 3 separate, massive 10-minute exposures where the flue gas temperature is suddenly spiked to 2,100 degrees Fahrenheit.
2,100 degrees. I was trying to conceptualize how hot that actually is. That is beyond the melting point of copper. That is the temperature of basaltic lava erupting from a volcano.
It's unimaginable heat for a residential structure.
I compare this testing protocol to the heat shielding on a spacecraft re-entering the Earth's atmosphere. The thermal stress must be unbelievable. But the text makes a crucial point here. It is not just a matter of the liner itself surviving and not melting into a puddle.
No, survival of the liner is only half the test. The true test, the entire reason this standard exists, is about what is happening on the outside of the chimney during this inferno.
Right, because of the pyrophoric carbon threat we talked about.
Exactly. During all of these tests, including those violent 2,100-degree spikes, the laboratory technicians are constantly monitoring an array of thermocouples attached to a wooden enclosure built closely around the outside of the test chimney.
To simulate the house.
This enclosure perfectly simulates the wood framing of a house. The liner must remain structurally intact, yes, but its primary job is to prevent the temperatures on that outside wooden enclosure from rising above very strict, highly conservative safety limits.
So the outside stays cool.
The goal is to ensure that even if the inside of your chimney is experiencing a literal volcanic 2,100-degree event, the 2x4s sitting just inches away inside your walls do not reach ignition temperature. The liner must contain the heat.
And while we are talking about clearances and wood framing, the text mentions a fascinating variation of this UL test called the zero clearance option.
Yes, the zero clearance test.
I had to read this section a few times because it seemed completely contradictory. Why does a zero clearance test even exist if we just spent the last half hour talking about how absolutely vital a 2-inch airspace clearance is to prevent baking the wood into pyrophoric carbon? Why would UL even test a zero clearance scenario?
I know, it seems like a contradiction, but it exists as a pragmatic, necessary recognition of reality by the engineering community. The chimney industry and the safety authorities know that out in the real world, outside the laboratory, there are countless older, masonry chimneys that were constructed completely incorrectly.
Before the rules were enforced.
Decades ago, before the Fulman and Mitchell research, builders routinely framed houses with the wood touching the brick, completely ignoring the clearance codes to save space.
So millions of homes are already built wrong.
Exactly. You can't just tear down millions of historic homes. So, the zero clearance test was developed as a retrofit solution. It tests to see if a modern, highly engineered, incredibly well-insulated lining system can be retrofitted into one of these old, dangerous, unlined chimneys and essentially compensate for the historical error.
So the insulation in the new liner replaces the missing airspace on the outside.
Precisely. If a liner passes the brutal UL 1777 zero clearance test, it scientifically proves that the material has enough insulative power to safely vent a 2100-degree fire, even if the exterior brick of the chimney is in direct physical contact with the wood framing of the house.
The heat simply cannot penetrate the new liner fast enough to become dangerous.
Exactly. It provides a modern, engineered safety net for historical construction mistakes.
That is incredible engineering. You are fixing a 100-year-old framing mistake from the inside of a dark vertical tunnel. So traditional vitreous clay is the standard, but what are the alternatives? Because pulling out broken, heavy clay tiles from a 50-foot chimney and trying to stack new ones down a dark hole seems like a massive, incredibly destructive job.
It can be a nightmare.
The text highlights a few alternative systems like stainless steel, but it focuses really heavily on one method in particular, cast-in-place liners. What exactly are these?
A cast-in-place liner is a brilliant piece of technology. It is essentially a highly specialized, lightweight, seamless concrete chimney created right inside the old existing masonry chimney.
Like poured concrete.
It uses a wet, pumpable, cementitious mixture that is heavily filled with specific, highly insulating mineral pellets instead of heavy gravel or sand. The text specifically mentions a mineral called perlite as a common aggregate used in these specialized mixtures.
Let's talk about the mechanics of this, because I'm fascinated by the physical installation process. How do you cast a perfectly smooth concrete tube inside a jagged, dark, soot-covered hole?
It is an ingenious, highly specialized process. First, the chimney is rigorously swept and prepped. Then the technicians lower a device into the chimney flue, typically a heavy, inflatable rubber former, or a heavy metal device called a vibrating bell.
Okay, so they drop a mold down there.
This former acts as the inside mold for the new liner. Once the former is positioned at the bottom, this cementitious perlite mixture is physically pumped in under pressure from the top of the chimney, completely filling the void space between the rubber former and the old jagged brick walls.
So it fills in every crack and crevice of the old masonry.
Exactly. It flows into the degraded mortar joints and solidifies the entire structure. The vibrating bell is slowly winched up the chimney, compacting the concrete mixture against the walls as it goes.
And then it dries.
Once the mixture cures and sets, which happens relatively quickly, the former is deflated and removed. What you are left with is a completely smooth, continuous, joint-free concrete flue liner that is permanently adhered directly to the inner walls of the old chimney.
And what makes this cast-in-place perlite material better, or at least different, than just sliding down a flexible metal tube or trying to stack new clay tiles? What are the specific performance advantages highlighted in the text?
It comes down to its unique physical properties. First, because it is joint-free, there are no mortar gaps to degrade over time. Total containment is achieved. Second, because it has a specialized lightweight concrete consistency, it's not entirely rigid like a traditional clay tile. It actually has a microscopic amount of give, or elasticity.
Why does elasticity matter in a chimney?
Because of thermal shock. When a massive temperature spike occurs, the material expands violently. Clay tiles can crack under that stress. The cast-in-place material can absorb the massive thermal expansion and the violent thermal shock without crapping or shattering.
And what about the insulation factor? You mentioned perlite. What exactly is perlite?
Perlite is a naturally occurring volcanic glass that has a relatively high water content. When manufacturers heat it to a specific temperature, the water vaporizes and the glass expands. It literally pops like popcorn, expanding up to 20 times its original volume.
So you are pumping volcanic popcorn concrete into the chimney?
Essentially, yes. And because the popped perlite is full of microscopic trapped air pockets, it is a phenomenal thermal insulator. Trapped air resists the flow of heat.
So it blocks the heat transfer.
The perlite provides such incredible thermal insulation that the cast-in-place material drastically stops heat transfer to the outer brick. It is so effective that these cast-in-place liners frequently pass that zero-clearance UL 1777 test we just discussed. They often do not require any additional insulating airspace. You can pump the perlite concrete right against the old historic brick, and it will keep the extreme heat safely contained, protecting the pyrophoric carbon hiding in the walls.
Okay, let's take a breath. We have covered an immense, exhaustive amount of ground here.
We really have.
So what does this all mean? We started this deep dive by calling the chimney a passive black hole, just a stack of bricks on the side of a house. But by walking step by step, deeply through just chapter 1 of the CSIA's text, we have uncovered a massive, dynamic, highly engineered system fraught with complex chemistry and extreme thermal physics.
It's a whole world in there.
We've talked about the critical historical shift from rigid material specs to rigorous performance standards. We've defined the terrifying, invisible reality of pyrophoric carbon slowly baking in our framing over decades. We've explored the century-old battle by insurance engineers to enforce the use of protective flue linings, the unimaginably punishing gauntlet of the UL 1777 2100-degree tests, and the modern marvel of pumping volcanic perlite concrete down a flue to save a historic home from its own architectural flaws.
It's incredible science.
And it is absolutely vital to remember that every single detail, every physical specification, every historical testing parameter we discussed today was completely sourced from the phenomenal foundational work compiled in the single CSIA publication.
It is a profound testament to the absolute depth of specialized knowledge required to properly build, maintain, and evaluate these structures. A masonry chimney is not just a hole in the roof. It is a highly tuned machine for managing violent chemical reactions and extreme exhaust temperatures. And it demands the highest level of respect, engineering, and understanding from the professionals who work on it.
Absolutely. And as we wrap up this deep dive, we have a very important, highly specific promise to fulfill.
Oh, right.
To Jerry Eisenhower, Regisner says hello, and he wants to pass along a massive, sincere, great work for your incredible ongoing efforts and your continuing massive contributions to the education of the chimney sweep industry. Your meticulous documentation in this text is genuinely making homes safer across the country.
Hear, hear. And as we leave you today, we want to offer a final provocative thought to ponder, building directly on the thermal science we explored in the text.
Yeah, let's leave him with something to think about.
We learned today that wood secretly bakes into highly reactive pyrophoric carbon over years of low-grade, seemingly harmless 200-degree exposure, hiding in the ceiling joists until the perfect moment to ignite. Today, in the modern era of construction, we are continuously making our homes more tightly sealed, more highly insulated to prevent heat loss, and packed with more high-voltage, heat-generating electronics and battery banks than ever before in the pursuit of energy efficiency.
That's very true.
So keeping that chemistry in mind, it begs an uncomfortable question. What other slow, invisible thermal transformations are happening right now, completely unnoticed, in the hidden, unventilated, highly insulated cavities of the places where we sleep every night?